Hello, and this is a review, and I'll re-emphasize it. I'll go over it a little bit in class next week before the exam on Friday, and this is for the second exam. So let us proceed with that, and I'll do my typical as I sort of view the exam itself and kind of come up with basically stuff about it. So two chapters: endocrine and the autonomic nervous system. So that's chapters 14 and 15, or 15 and 14 if you want to do it in that order. So we start with endocrine. What an endocrine is a system that basically transports hormones, which are either fat based or protein based, to a variety of target organs. That's really what it is. They go directly into the bloodstream. They are effectively a combination of different activities would be the best way to describe it. Okay, so they go into the bloodstream, they find target organs. Most of them are proteins, not entirely so, but certainly that's a fair thing to say about them. And typically, the structures that produce them are relatively small compared to the impact that they have. If you think of the pituitary or you think of the parathyroid hormones that are there, they're effectively classified by what they're made out of. So proteins obviously amino acid based, where steroidal hormones are basically made from are cholesterol based. So in some way, shape, or form, they come directly from cholesterol. That would be the best way to describe them. And we characterize them as being either water soluble or fat soluble because of those things. Or if you want to call it hydrophilic and hydrophobic, that's fine too. So if you think of the water soluble based hormones, they can't enter the cell because they're not membrane compatible. So they have to function extracellularly. They effectively, in order to enact what they do, they have to enable a second messenger system. They are the primary messenger, okay? But in order for them to act, they have to utilize the secondary messenger system. That's there. And typically, again, that's cyclic AMP, certain enzymes, calcium, etc. Those are the types of things that they utilize internally by way of second messenger systems. Okay. Whereas the lipid soluble ones are membrane compatible. They can transfer through the membrane, or transport rather, through the membrane, and in doing so, they're able to contact receptors that are located within the cytoplasm. They complex in the cytoplasm in that sense, rather than going through that whole G protein passageway that you've seen any number of times. And and effectively that complex of the receptor and the messenger inside the cytoplasm is able to then transport through the nuclear membrane and directly enable DNA to to start transcription and then subsequently obviously translation to generate whatever the end products are going to be. So that's really where it looks like. So one is a G protein passageway, those are the extracellular or water soluble, and the ones that are an internal passageway by way effectively cytoplasm and then into the nucleus are, or rather is, the mechanism by way of transcription or translation for the lipid soluble based hormones. So I think that those are all important features that are there. So, and there's a lot of different stimuli. So, the hormonal release is governed to some extent by other hormones. It's governed, and these are three factors, are governed by humoral factors, blood levels, let's say calcium or sugar in the bloodstream, just would be very easily recognizable examples. And then even neural stimuli, and that's sort of the override, if you will. And that's why these two systems are good to look at together by the autonomic nervous system. So, for instance, an override of something like that would be, let's say, the vagus nerve. Okay. The vagus nerve is obviously a portion of the nervous system, releasing acetylcholine, decelerating the heart, and it would offset, let's say, sympathetic activity from epinephrine and norepinephrine. So it would alter endocrine activity. Or you could look at something like the fight or flight response. So those to a certain extent would I maybe the fight or flight response is a little bit better example of this, I would think. So if you think of it this way, that the vagus nerve is basically acting directly on the heart, and the fight or flight system is acting directly on a variety of other endocrine systems and really challenging them. So I think that's probably a better example of a nervous system override than just basically pure autonomic, which would be the vagus system. If you want to think of those two when they're there. Now, if you want to think of a hormonal response, there's a variety of hormones. Let's say, when you have low levels of estrogen or progesterone triggering GnRH, the gonadotropin release hormone. Okay, that's a hormonal mechanism that's there. And a humoral mechanism, as I said before, would be like calcium or sugar that's in there. Let's think of specific hormones that are part of it. Okay, so if we look at first, we look at the posterior pituitary. Really have there. There are a number of hormones that are released. Most of them are in that category of RH and IH, release hormones, inhibiting hormones, master controls on the pituitary. The two true neurotransmitters and those are certainly uh, hormonal activity. The other ones are oxytocin and antidiuretic hormone or vasopressin. So those are all hormones, technically speaking, because they are released into the bloodstream. So releasing hormones or inhibiting hormones, whatever they are, whatever category, whether it's GnRH, whether it's thyroid stimulating or thyroid inhibiting hormone, doesn't matter. That will impact the pituitary. Plus, the actions of oxytocin and antidiuretic hormone will all technically be considered hormones that are produced. So the releasing hormone is still a hormone, but as its name would obviously suggest. So what do those things do? Well, oxytocin we know it does play a certain role in lactation and perhaps some other activities, but principally it's stimulating in that positive feedback cycle with regard to delivering a baby by way of the birth canal. The antidiuretic hormone specifically acts on certain areas, and its most prominent activity, although there's other things that it does, is really being able to sort of pull water back in. So it's effectively decreasing the volume of water in the urine. So it's effectively a concentrating mechanism. And as its name would suggest, antidiuretic, meaning it limits diuresis or it limits urination. So it pulls water back into the system. So you should know all of those 6 hormones that come from the adrenal cortex, and not the adrenal cortex, from the pituitary. So the pituitary has human growth hormone, adrenocorticotropic hormone are there. Okay, thyroid stimulating hormone when it's act on the thyroid, and then those are one group of 3. The other group of 3 effectively all are reproductively oriented, and that would be FSH, LH, and prolactin. You got to know those 6. Those are very, very significant. Okay. Really, because if you think of the pituitary as the master gland, you really need to know all the substances and to a certain extent what they do. Growth hormone, generically speaking, favoring growth and the utilization of fats as the energy source for the growth. Thyroid stimulating hormone, increasing activity of the thyroid, adrenocorticotropic hormone, increasing activity of those 3 areas of the adrenal cortex, and the other 3 with their roles. FSH, follicle stimulating, think ovaries and testes. Luteinizing, think of the different uh, hormones secondarily that they produce, the estrogen, testosterone, and progesterone. And the prolactin, obviously, as its name would suggest, lactation, but there's other aspects of it that are there sort of in maintaining overall reproductive health, if you want to think of it that way. And remember, the oddball is when we see that inappropriate lactation, that's one of those little hidden signs that doctors look for and go, if that's happening, there's something going on, most likely in the pituitary gland, suggesting pituitary tumor. So you can think of human growth hormone and is a targets many cells, where thyroid stimulating hormone is just about the thyroid. So you think of that as which ones target the most, have the most targets, where are the most receptors, and certainly human growth hormone and its companion, sort of, although they work to some extent oppositely in the sense of what they utilize for energy, would be insulin, where a lot of cells have receptors for those. So those are all of the things that are there. And we looked at some of the deficiency disorders, and famously the term diabetes, which means the great thirst, we always just, oh, but people with sugar problems. Well, again, classically, although it's comparatively rare, it's not that common a disorder. Diabetes insipidus, or salt diabetes, has to do with the insufficient production of antidiuretic hormone. And again, thankfully we can now make that genetically, but that's the specific name, where diabetes mellitus is classically the sugar diabetes. And again, in the old days, it was classified by what was in the urine, whether there was excessive salt or whether there was excessive sugar. We spend time looking at the thyroid and basically sort of what goes wrong. And for years, what went wrong up until the early part of the night, certainly in the 1900s, and in the 1800s, and then into the 1900s, was the abundance of people with goiters. So we understood then that a certain small amount of iodine was important for thyroid function, and what it did was it allowed that globulin, which is what the thyroid produces, to be processed into active thyroid hormone in the form of T3 and T4. So it was that interrupted that sort of passageway, going from low thyroid hormone in the blood, which would then be recognized by the posterior pituitary and produce it would produce factors that would induce, or thyroid releasing hormone that would trigger thyroid stimulating hormone that would stimulate the thyroid, would make the globulin. But if they didn't have the iodine, it would just accumulate and cause this swelling called a goiter. And unfortunately, your body didn't get the message that, oh, we've got plenty of globulin, we just don't have enough iodine. All it understands was there's insufficient T3 and T4, so it was a vicious cycle that was there, and that caused that enlargement. That's why we started using iodized salt. And thyroid hormone is where, if we think of human growth hormone targeting having receptors on nearly all cells, well, thyroid hormone, not the thyroid stimulating hormone, that's just the thyroid, but thyroid hormone in the form of T3 and T4, that targets an immense number of cells. Why? Because thyroid function really kind of is the companion for all, whether it's cardiac, whether it's kidney, whether it's reproductive, whether it's metabolic, it doesn't really matter. It keeps it at the appropriate level. So when I call it the companion, and really to me, there's always, thyroid has been sort of like the overall governor of metabolic activity. If you have an excessive amount of thyroid, you metabolize too quickly. If you have an insufficient amount of thyroid, you metabolize too slowly, and you get attendant problems with hypo and hyperthyroidism. And I think we probably see a little bit more in the way of hypothyroidism, and it's a little bit easier to treat. We see it from dysfunctional thyroids. We certainly see it from thyroid tumors. And because typically thyroid tumors make that area of the thyroid not function. When we look at them, we call them cold spots because there's not metabolic activity. As opposed to most tumors, we look at hot spots where there's excessive activity. And so the treatment is removal of the tumorous tissue or the thyroid in its entirety, and supplementation with thyroid hormones, which has been around for a very long time. Okay, so we used animal-based thyroid hormones, and now we can make it certainly laboratory-wise relatively easily. It's the hyperthyroid activity, trying to slow that down. Those medications have a fair amount more side effects. Remember, when we look at the adrenal cortex, multiple layers. So you have, and we're not talking about the medulla, which is about the sympathetic nervous system. That's the next chapter. And And when we look at the adrenal gland, okay, that you have those three outer zones that are there. I don't think you need to know the names of the zones. I'm going to look through the test to make sure. If not, I'll share them with you. But the external portion of it, the cortex, the most external layer is aldosterone. The middle layer is the cortisol. And that internal layer is those androgen-like hormones, the testosterone or androgen, like testosterone type precursors or hormones that are there. So the outermost layer is about aldosterone. What does aldosterone do? It inserts little openings or little passageways into the collecting ducts and the distal convoluted tubules to resorb sodium. And then when sodium is resorbed, okay, then that water will accompany it on its journey. And it's under control nearly exclusively, though there's some other mechanisms, on that very famous renin angiotensin aldosterone mechanism, which we're going to explore a lot of times. But that's really the significant pathway. So it's the renin angiotensin mechanism that we look at. So renin is, to me, is the critical player with regard to that more than anything else. And that's the chemical that's produced by the kidney. So it's in that internal zone, okay, where women produce testosterone and androgen. So that's where we begin to see it. It's only in that internalmost zone of the adrenal cortex, just outside the adrenal medulla. The pancreas, insulin, and glucagon, which are its endocrine function, again, just like the gonads, it's a double duty gland. It's both endocrine and exocrine. We're dealing with the endocrine functions, and digestive, we deal with the exocrine functions of the pancreas. And so the big players there are insulin and glucagon. When we look at something like secretin, which we'll look at in digestive, that is an exocrine secretion, but not an endocrine secretion. So it's a little bit different. Okay, that's there. So the islet cells, the beta and alpha cells, the beta cells are insulin, the alpha cells are glucagon. They're like an interesting work oppositely kind of a team approach that help to regulate sugars that are there. Glucagon effect is specifically on the liver to raise blood sugar, where insulin is on obviously multiple cellular structures, multiple areas of tissue to lower the blood sugar. So it's effectively all cells and lowering the blood sugar. So when we look at the different kinds of diabetes, and I try to make it simplistic, I don't want to get into, like I said, I have a lot of expertise, I'd like to think, and knowledge about diabetes, having treated it for so long, and it's constantly changing. And to be honest, I haven't been in a conference where the sophisticated views of diabetes have been presented in the last 20 years. So I'm trying to give it to you from a sense of what you'll need to know, both for the completion of the course and for some of you going forward, if you're particularly going into medical fields. So when we talk about type 1 diabetes now, in the old days we called it juvenile onset or juvenile diabetes. Really, now we've separated them. Type 1 means we're not, for whatever reason, not producing insulin. Okay, it's something involved with the production. Either we're not making the insulin or we're making something that's effectively faulty. That's the problem that's there. Where type 2 diabetes is much more about the inability for the insulin to be utilized at the receptor level. Damage to the receptors, problems with the receptors, something involving the lack of binding with the receptors. Actually, even though the insulin is there, look at it that way, it's not doing the job at the cellular level to get the sugar into the cell. So, and that's what we see with it. But in both instances, pardon me, my voice, drinking coffee here at home. Pardon me. I took allergy pills and I'm very congested this morning. So sorry. Nevertheless, when you talk about diabetes, what is the big way we look at it? Obviously, the great thirst, but it's characterized by high levels of blood glucose and frequent urination. That's really the big players that are there. Are there? Do we have great thirst because that's its name. Absolutely. But the big players are frequent urination and high levels of blood glucose. Those are really the starting points, I think, more than anything else, because the excessive glucose in the urine effectively is an osmotic diuretic. It pulls fluid into the urine, and we have a limited storage capacity in the bladder, and we have to get rid of it. So it's accompanied by a great deal of thirst. That's the polydipsia. Because your cells are starved for glucose, you get the polyphagia. You get the fatigue because you're not getting the energy production associated with ATP. But I mean, the major characterization is, in the way we used to call it, is symptomatic hyperglycemia. The symptoms being frequent urination and other symptoms associated with hyperglycemia, high blood sugar, consistently there. What happens long term in that? We get a lot of problematic fats because we have to utilize fat really in sort of the pecking order of what we do nutritionally. First, we utilize carbohydrate or carbohydrate based products. They're favored. They get utilized first. They're relatively easy energy use. Then comes fats. Fats have a lot of bang for their buck. They're a great energy source. That's the good news. The bad news is, depending on the kind of fats, and when you're using fats extensively and excessively, you get harmful fatty byproducts, typically referred to as ketones and keto acids. Trans fatty acids, if you want to think of them. You hear about them all the time. Nutritionally, you hear about them in food advertisements, or if you look at various kinds of whatever familiarity you have with nutrition or dieting or different foods in the advertising process. They are a problem. And what they do is they are sort of the foundation for the kind of fats that are highly inflammatory and have an alarming tendency to augment or enhance the amount of damage that are done to blood vessels. That would be that would be sort of the way to summarize it. Again, to me, I've always found that the fatigue issue, that's something we see a lot in diabetics, is kind of hidden. That's there. When diabetics are well controlled, they function as well as you and I do normally. But to me, the big problem is that you just can't produce a sufficient amount of ATP on an intracellular basis. A couple of other little side notes of other hormones that are important. Remember the erythropoietin that we see inside the kidney, just in the same way that and the erythropoietin works, and we just did the blood unit stimulating the bone marrow, where renin is a little bit different. That is specifically on that, and it certainly is a hormone because it goes into the bloodstream, but that's on that renin, angiotensin, aldosterone model that's there. When we begin to look more closely at repro, we're going to see about a fat called leptin. Leptin is essential because it plays a really significant role in the appropriate onset and the continuance of the female reproductive cycle. Okay. And so if you have inadequate fat levels, women can't start menstruation. We're going to go into that in a considerably greater degree of detail when we look at reproductive physiology, because I have a lot of comments about that from not with my daughter, but with my I don't know whether I've shared that anecdote with you about the figure skating, and we see it with gymnastics and other fields with regard to trying to delay the onset of menstruation. Highly inappropriate's the wrong word. To me, it's criminal, but that's just me. That's there. So what happens? There's other of these that are maybe less. We talk about less than thyroid hormone or estrogen or progesterone when we start talking about something like atrial natriuretic peptide. It's it's something that combats aldosterone's there to increase fluid and increase blood pressure. But what happens if we have an overload of fluid? Well, we have an overload of fluid, it stretches the atria. The atrial lining cells then release an interesting peptide called atrial natriuretic peptide. Natri means sodium, and so it's sort of like the opposite of aldosterone. It causes sodium to be excreted, not to be retained, but to put more of it into the urine and pull water with it that way. So it works a little bit of opposite of that. And again, that's one of those lovely homeostatic mechanisms that are there. So I think that that's all part of it. Don't forget the role of the thymus, because it's all about T cells. Many of you have immuno. We're going to start the immunology unit right now, in as we approach the semester break, and probably spend maybe a day or so talking a little bit about immunology before I go full bore into it. And I think it's a difficult unit. I always have to sort of kind of do it my way in an abbreviated style when Dr. Mauer's doing immunology. Because I don't know what he goes over at his course, and perhaps even this year I'll ask him a few things about that to make sure that there's not a heck of a lot of duplication. And obviously, not everybody's taking that course. When we look at the autonomic nervous system, understand that that's the control of smooth muscle of blood vessels. And it's strictly sympathetic. That's to me, the big issue with what's unique about sympathetic versus parasympathetic. It's not a homeostatic relationship directly. It's not like the two are playing tug of war with one another like they are with reproductive functioning. It's all sympathetic. Therefore, blood flow is controlled by the sympathetic. Whether it's active or inactive is the determination. Is the direct determining factor, and therefore, that means it's all about the kidney. That has to do with sympathetic nerves. So there'll be a lot of questions about fight or flight. What happens? Okay, that's the division. That's the sympathetic. If you think of what happens in fight or flight, and I say it all the time, the opposite is parasympathetic. Pupils constrict, okay, in parasympathetic. But when you're in sympathetic fight or flight, you've got to be able to get the big picture. Your pupils dilate, your eyes are wide open. You're in the process of trying to escape or deal with a dangerous, life threatening situation. Your blood pressure elevates, your heart rate elevates, your bronchi dilate. You need maximum oxygen. You're diverting the blood flow to your heart maximally into your skeletal muscle so you can run and be very, very active. You eliminate, for all intents and purposes, nearly all of the blood flow other than what's necessary to maintain the viability of to cool off the core, which is going to be awful hot. It really is. It's more about perspiration than blood flow to the skin. The blood flow to the skin is sort of taken away, but in order to get rid of some of the inevitable heat that's produced by the muscles, therefore you have perspiration. If you want to think of it that way. So you have minimal gastrointestinal and kidney function. It's just, if you just remember those kinds of things, you'll know what's going on. And the prolonged effect comes from that sympathetic stimulation of its remote ganglion, the one that we call the adrenal medulla. And the prolonged effects come from both epinephrine and norepinephrine that are produced there. Okay. So that's all the important aspects that are there. So what happens in flight or flight? What do the pupils do? Do they constrict or dilate? Well, they dilate. What happens to the respiratory passageways? They dilate as well. What happens to the kidneys? Their activity is highly limited. The blood flow is almost negligible, comparatively speaking. Know the neurotransmitters, pre and post ganglionic. All the preganglionic neurotransmitters are acetylcholine. Their acetylcholine is the neurotransmitter in the postganglionic in the parasympathetics. The only one that's the oddball, save one example, is in the sympathetic where it's norepinephrine. The oddball is to the sweat glands where it's acetylcholine. Remember the names. All the preganglionics are called nicotinic receptors. All the postganglionics in the parasympathetic system are called muscarinic receptors. The ones, because of epinephrine, or in this case, norepinephrine, in the old term being adrenaline, are called adrenergic receptors. Again, with the exception of that one oddball, okay, that happens to be the acetylcholine and it's muscarinic for sweat glands. That's it. Mhm. So you got to be familiar with all of those. So we find nicotinic receptors in both. Adrenergics, we have alphas and betas. Okay, and we have plenty of those, as you know, some examples. So what happens to what causes bronchodilation? Beta receptors being stimulated, but they're not beta 1s, they're beta 2s. What happens with your glandular secretions in fight or flight, like saliva? We don't need that, can't breathe. Clog things up. So you get a very, very dry mouth. So it decreases salivation that's there. And when we talk about blood pressure, what's the major impact on it? Sympathetic tone. That tone, and whenever you use the term tone, whether it's muscle tone or nervous system tone, it's that level that it maintains. Whether you're awake or asleep, you're always, obviously, if you're asleep, your blood pressure doesn't go down to zero because you wouldn't be able to survive. It's just everything kind of slows down as your body sort of regathers itself, does a lot of the processing, if you want to think of it that way, whether it's urination or defecation, which you typically most of us end up doing first thing in the morning because all that processing has gone on. So, what do beta adrenergics do? When it's beta adrenergic ones, okay, those are the ones that focus on the heart. Okay. And remember, when it's sympathetic, it's heart rate and force of contraction. When it's the effects of the vagus nerve through the parasympathetic, that's just decreasing heart rate. That's there. So all of those are part of the things that you have to know. Okay. So effectively, what's the unique part about the adrenal medulla, and we say it all the time, it's really just a remote ganglion for the sympathetic nervous system. It's the only one that's not next to the spinal column. So I think you have to know all of those things. What did we use traditionally in surgery? We use something called a sympatholytic agent. It's called atropine. And now it may be something different that's used today because it had a fair amount of side effects. Effectively, it blocks the basically it's not sympatholytic, but it's parasympatholytic. And we'd use that to basically block salivation. So if you had to intubate somebody, you could use it. That was a standard part of the preoperative orders that were there. And maybe there's a more advanced substance. I haven't ordered that stuff and really we didn't order it other than during residency. That's something that the anesthesiologist would order. So when you increase sympathetic activity, whether you block parasympathetics, that's parasympathetic lytic, or you increase sympathetics, that's sympathomimetic, it mimics sympathetic activity, you're going to decrease salivation. If you increase sympathetic activity, you're going to decrease urination. So those are really ways to understand. So when you use those terms, sympatholytic and sympathomimetic, or parasympatholytic and parasympathomimetic, try to remember. And I think that's it. Enjoy. More information next week. Bye bye.